So hello everyone. So today what I'm going to discuss is one of the most important questions that have been asked frequently, maybe 4 or 5 or something, 15 to 20 marks you will definitely get in CSIR, either GATE, whatever exam you take, and that is the important topic is pericyclic reaction. So you can't miss that topic. That's important part, and pericyclic reaction is a major part in organic chemistry. So before I going to start, I would like to say one point that I have already made numerous number of example with proper explanation, and the topic or the concept you need, it is already been there. You can you can see the previous videos that have been already shared with you. So what I am going to discuss in this video, the basis upon which the pericyclic reaction is based on, that I am going to discuss. So there are a number of methods by which pericyclic reaction can be explained, and one of them is the frontier molecular orbital method. It is known as FMO method. What are the other concepts that you have to know, or maybe be a little less? That is the Huckel-Mobius system. It is very interesting, and I would like to share it with you in my next videos also, I would like to say. And the other method is symmetry correlation, that is the point, and perturbation method. So these are the method, but my point and everyone else also point is the frontier molecular orbital method that has gained so much popularity because of simplicity. But the simplicity of Huckel molecular orbital method, this is based on. So let's start with this topic. So pericyclic reaction, what I have already told, frontier molecular orbital. Frontier molecular orbital. Okay. The term itself says that you have to be careful with molecular orbital. Okay. Before I going to discuss this frontier molecular orbital, let me say some point about pericyclic reaction. The term itself says that that's the term, periphery. The reaction involves the periphery of the substrate. That's why it comes peri. And why it is cyclic? Because it involves a cyclic transition state. That's why the name comes pericyclic reaction. There are several other major points that you have to I hope you already know, but I want to say is that this type of reaction is independent of my solvent, my catalyst. These are the things that doesn't affect the pericyclic reaction. This is totally controlled by the symmetry. Symmetry of what? Symmetry of the molecular orbital. That discusses it. Reaction, stereochemistry, whatever the condition that is favoring or not favoring, everything depends upon the molecular orbital. That's why it's based on molecular orbital method. So the basis of molecular orbital is that when I have two orbitals, let's say SS, so it will form a bonding molecular orbital and as well as anti-bonding molecular orbital. So the pericyclic reaction involves basically pi molecular orbital system, not sigma molecular orbital system. Now the pi molecular orbital system, there is a theory, Huckel molecular orbital, and the approximation is that we are only considering the pi bond itself, not the sigma bond, because sigma bonding itself is another part. We are thinking that pi bonding is not depending upon the sigma system. So we are only interested in the pi molecular orbital. That's the important point. Now take some little small one example how this molecular orbital is formed in simple system. For example, one of the easiest or simply I can write ethylene that has one pi bond. Okay, so the point is that there is a one pi bond. You can see easily. Okay. Now you have to draw pi molecular orbital diagram for this molecule. So how to draw this? That is the important part. Okay. Here I have two carbon. One carbon is there, one carbon is there. So how one pi molecular orbital will be formed? Definitely it has a 1p orbital and it has a p orbital. That is going to form a pi bond. So the basis is that if my pi bond is there, 1, and there is a 1, let's denote the symmetry phase. it doesn't, sometime you may see there is a plus or minus, but that doesn't mean there is a charge. It denotes the symmetry present in the molecular orbital. So these two p orbital will form a bonding molecular orbital, pi bonding molecular orbital, and another will be pi anti-bonding molecular orbital. So generally, you will see in book they don't see write like this. They easily just write this way. One p orbital is formed bonding molecular orbital, another is anti-bonding molecular orbital. What do you mean by bonding and anti-bonding molecular orbital? Basically it involves if my p orbital overlap with the same phase. You can see there these two are in same phase in the upper side also, lower side also. So this is formed a bonding molecular orbital, pi bonding. Okay, and in the upper case here the bonding is not bonding. There is no bonding actually, because the symmetry of these two p orbital are not matching. That's why it forms an anti-bonding molecular orbital. So what is the characteristic of anti-bonding molecular orbital here? Here there is a nodal plane. Okay, see there is no bonding. That's why it's called anti-bonding, and this is bonding electron. One more thing, here the y-axis is the energy. So my pi bonding molecular orbital is less energetic. That's why it's more stable. Anti-bonding is higher stable. That's why upper in energy. The second point that you have to understand, which is called HOMO and LUMO of a pi system. So basically in ethylene there is a 2 pi electron, and you know Pauli's exclusion principle. Another thing that these 2 electron will occupy this lower energy molecular orbital. So that's why there will be 2 terms, H highest occupied molecular orbital and lowest unoccupied molecular orbital. So the term basically itself define itself, that is highest occupied molecular orbital. Here it is pretty easy. My highest occupied is here, so it is HOMO, and it is unoccupied, so it will be called LUMO. It's basically easy to understand, that is HOMO and LUMO. One more thing I forgot to say, that whatever I have already till now discussed is basically I am thinking that it is a thermal condition. My molecule is in ground state, and thermal condition I am applying for any reaction. So that's why my HOMO is here and LUMO is there. Let me take another example, so it will be easy to the term you will understand more easily. For example, the one of the most important molecule in pericyclic reaction, it will be everywhere, that is 1,3-butadiene. So that is 1,3-butadiene. So basically what you need to know, that there are 1, 2, 3, 4. This is forming my pi molecular orbital. So since there is a 4, so my molecular orbital will consist 4 pi orbital. Okay, and since there are 4, so it will have 4 molecular orbital. Each will denote as Chi1, Chi2, Chi3 and Chi4. So what I am trying to say, my butadiene has 4 carbon with 4 pi electron. It will have 4 pi molecular orbital. Now the most important part, please watch carefully. My point is to how to draw the molecular orbital here. So basically you can draw first 4 pi orbital easily. I am not doing any phase. I am not showing here any phase. So just draw 4 pi orbital which will gonna form molecular orbital. So this is my basis. Okay, so this is our. So since there is a 4 carbon system, so there will be 4 pi molecular orbital. Now let's define the phases and see what happened. So basically this is my energy, and the point is, as you go upper in energy, the number of nodal plane increases, so the system's energy also increases. So how many nodal plane is there? That is the point. If it is my that is Chi1, that is ground state, there is no nodal plane, all is bonding. So it will have no nodal plane. So there is, see, there is same phase. So it can be represented as a one wave like this. So it is my psi1 with no nodal plane. So basically you have to, if it is easy to understand, remember like this. First with 0 node, then with 1 node, then 2 node, then 3 node. So it will be definitely my highest antibonding molecular orbital, and this is bonding. So here there is no node. One more thing you have to notice, that there is a sigma symmetry as there. You can easily see that is a mirror symmetry. It is just mirrored to this. So that the other system, how does it look? What I already told, that it will have one nodal plane. So let me draw it here, nodal plane. So basically one nodal plane, what does it mean? It means that there will be mismatch of phase. So I can first draw it like this. So it will be mismatch in phase, that's why it will be look like this. And these are bonding, so it will have matching in phase and it will have matching in phase. Can you see any symmetry element here? Yes, of course, yeah, there is one symmetry element, that is C2. How? If my symmetry element C2 is there, if we operate like this, so it will, this point will come here and this point will come here. So my psi2 has a C2 symmetry and it has a mirror symmetry. So this is generally followed upper level also, upper molecular orbital. So my next molecular orbital, it will contain mirror symmetry. One more thing I would like to say, that suppose you don't know where will be my nodal plane. I am showing it here. What you know is that there will be one nodal plane. So by mistake you thought that why not here there will be a nodal plane. Let's draw it. I can also draw like this. This will be my bonding. Here also there is a one nodal plane, but this can't be the molecular orbital. Why? Because it doesn't contain the C2 symmetry. That's why you have to be always careful how to eliminate the option. It can't be the my psi2, because though it has a one nodal plane, but it doesn't contain C2 symmetry. So you can easily eliminate this option. Now let's take the psi3. What will be the node? Number of node? That will be two nodal plane. Okay. So here I am drawing like this. Let's see that there is a mismatch will be here because there is a nodal plane. It will be like this. This is bonding. It will be like this. Anti-bonding. It will be like this. Again you may think that why not I am taking this nodal plane like that. Then you will not find mirror symmetry. You can do it by yourself also. It may be a practice. So see, there is a mirror symmetry. You just pass a mirror here. You will see the same. Now coming to this point, psi4, there will be three nodal plane and it's easy and trivial. So there will be nodal plane each and every. So this is anti-bonding and again anti-bonding, again anti-bonding. So that's how I have generated the 4 pi molecular orbital present in 1,3-butadiene system. Now let's fill the molecular orbital with my pi electron. How many pi electrons are there? Definitely 4 pi electrons there. Let's just put 2 here and 2 here. So what will be my HOMO? Since it is the highest occupied molecular orbital, it will be my HOMO, and this is unoccupied, this is my LUMO. One more thing, it is in thermal condition. Now let's say I have given a molecule and it is treated with H nu. So what will happen to in presence of H nu? Basically electronic translocation from this HOMO to LUMO. I am not drawing this molecular orbital again. So this, there will be 2 electrons and this will be 1. So in the presence of H nu, you can see that my highest occupied molecular orbital is not this one, because I have a higher one with a filled electron. That's why now it will be my HOMO. So this is one of the concepts that has been asked in CSIR December 2017. In presence of H nu, what will be my HOMO and LUMO? So let's see the question and answer. Okay. Before I discuss the question that has been asked in CSIR 2000 December 7, let me discuss some points that we will find easy. So in exam, you can't draw this every time. It will be difficult to solve the question and time is very much costly. So how to generalize the system? So you have to remember the one point. If my psi n is a pi molecular orbital, the number of nodal plane will be n minus 1. What I am saying, if it is my psi n molecular orbital, there will be n minus 1 number of nodal plane. Let's see in this example. For example, if I take psi 3, so 3 minus 1, there will be 2 nodal plane, and you can see, yes, there is 2 nodal plane. So the other point that you have to remember is that it is always this mirror symmetry consecutively C2, mirror and C2. That is, if my psi n and n is odd, there will definitely be a mirror symmetry, and my psi n is if n is even, it will contain a C2 symmetry. These 2 points you have to remember. What is the other point? If my condition is given thermal and my system contain n number of that is 6 pi, say 6 n equal to 6, 4 pi n equal to 4, then there will be, what will be the HOMO? How to find it very easily? There will, in thermal condition, it will be n by 2 molecular orbital psi n by 2, that will be our HOMO, and consecutively n by 2 plus 1, that will be our LUMO. Let's see this system. For example, here I have drawn for molecular orbital butadiene, that is 4. So if I divide it by 2, psi 2, that will be my HOMO, and I have already shown it. And what will be my LUMO? N by 2 plus 1, that is, I am writing here n by 2 plus 1. So 2 plus 1, 3, psi 3 will be my LUMO. So remember one point, I am considering a thermal condition. If you are given photochemical condition that is treated with H nu, then you know that my HOMO in this system will be the upper one, that is n by 2 plus 1, it will be my HOMO. Since it's constant 1 electron, it is sometimes also called SUMO, singly occupied molecular orbital. So these are the points you have to remember. How many nodal plane is there, it is symmetry, and how to find the easily HOMO and LUMO in a pi molecular orbital system. Now let's see the question, it will find me easy. So let's discuss the question. So before I discuss the question, the important part that I have to remember, I have already told, that is the symmetry element, and what is my HOMO, and how many nodal planes are there. These are the 3 important points. So the question is they have asked is they have given a 6 pi electron system, and they have condition H nu. That's why I am telling, please read the question very carefully, to give this kind of cyclic system. Okay, so you don't need to know this, what is this reaction, we will discuss it very soon. Okay, so they have asked in this question, what is my HOMO in this condition of this system. Okay, so what I have already told, if my system n pi electron, here it is 6 pi electron, there will be my n by 2 in thermal condition, it will be my HOMO. I am telling again, if my system n pi electron system, that will in thermal condition, it will be HOMO n by 2, psi n by 2. So if it is a thermal, if it were a thermal condition, my psi 3 would be the HOMO in thermal condition. But you know that in presence of H nu, it is not psi 3, but n by 2 plus 1, that will be my HOMO. So it means my psi 4 is the HOMO. Now let's see some important point about psi 4, by which you can easily pick out the correct option and eliminating the wrong options. How to find those options? For example, you have already understand that my psi 4 is HOMO. Okay, no problem with that. Now you know number of nodal plane, there will be 4 minus 1, n minus 1, that is 3 nodal plane. So there will be 3 nodal point, that is the important part. What is the other important part? The other thing is important is that since it is psi 4 and n is 4, that is an even number, it will have a C2 symmetry. So I am writing it here. You have to find where C2 symmetry is there, and again there are 3 nodal plane. So by just looking at the 4 option, you just try to find out these options, and you can eliminate the other option. Let's see this. I will discuss each an option very critically. Let's first, it is easy to understand nodal plane, that is 3. Here, how many? Mismatch in orbital, 1. These are matching, no nodal plane, there is a 1, that is 2. So it can't be the correct option. I am just eliminating it. Now let's see the second option. Same phase, opposite phase, 1 nodal plane, same phase, opposite phase, same phase. there is a 2 nodal plane. It can't be the option. See, it's pretty easy. Now let's come to this point. There is only 1 nodal plane, so it can't be the option. How many? 1, 2, 3. It's the option. You don't need to even see the C2 symmetry also here. But if you also see the C2 symmetry, you will find here C2 symmetry. You can easily check it out. So that's the correct option. I hope you find it very interesting and pretty easy to find this kind of problem in future also. So I have told the basic concept that the foundation on which the pericyclic reaction is developed, the frontier molecular orbital, and this is one of the most important topic, as you know. So I would like to say, please watch my previous videos, and there are lots of questions I have discussed, and I'm pretty sure you will find very useful this concept in exam. So thank you for watching, and please subscribe and share with your friends. Thank you.